Okay, off we go. So, yeah, here's where we were last time. We were talking about cross products. I mean, just barely, right? I had just brought up cross products, wrote down the definition, and then wrote down the formula that I think in practice you should use to compute cross product, and even really to think about cross product, because it shows this very strong connection to determinants, even though it's a little bogus, right? It's a little sloppy. But nevertheless, I think much better than the formula on the left there. Okay, now there is a related fact that we're going to talk about, very closely related fact, and I like being able to get all this algebra on the screen all at the same time. Suppose you want to do this little computation here for no apparent reason. Some arbitrary vector C to be dotted with a cross product of A and B. And what do you get? Well, this is pretty easy to write down. There's C, just some vector with coordinates. We have this existing formula here for the cross product. And so having written that down, we haven't really done anything here. But then look at how you would compute this dot product. And what you would write down, for example, the first term you would write down would be this times that, which you'll notice is the top left element times the determinant of the submatrix. And then the second thing you would write down is, that times that, which is the second element times the determinant of its submatrix. It's even got the minus sign in here from the whole checkerboard pattern thing, right? So in fact, this what we're going to call a triple product can be computed directly as a determinant. And that's not a fake determinant. There's no bogus nonsense. That's a straight up, no asterisk determinant of a 3x3 matrix, right? So this is a really cool formula, and one of the big reasons why we care about this formula is because we don't understand cross products yet, but we do understand dot products and determinants. We know a lot of stuff about dot products and determinants, and so having a relationship that relates stuff we're interested in to stuff we understand is a foot in the door. And very, very valuable, very, very important to be aware of. Okay. All right. So now I'm going to, at this point, we're going to be going through a bunch of facts about cross products. These facts all have proofs. These proofs are all super cool. But, yeah, they're really linear algebra. And time is tight in this class, and tough decisions and all that, right? I can't do everything in class. So what I'm going to do here is I'm going to go through and talk about the theorems and why they're important, that kind of thing, right? And then I'm not going to talk about the proofs. And this is not I want you to read them on your own and you're responsible for them sort of thing. I'm going to officially absolve you of responsibility for these proofs. Now, that's just because I feel like there's enough substance in the proofs that I wouldn't really quite feel comfortable holding you responsible for it and not going through it, right? That said, I do hope you will look at them. Because there's some tremendously cool ideas in these proofs, right? There's a lot of intuitive connections that you'll make if you go through and study these proofs. So just to try to persuade you, just to try to lure you into maybe looking at these proofs as we skip them, right? Later, of course. I am going to show you the proof of this first fact. So this first theorem we're going to talk about says cross product is always orthogonal to both of the input vectors. Cool fact. Very heavily used fact about cross product. One of the big things we're going to find a lot, especially coming up soon, is when I have a couple of vectors, how do I find a third vector that's perpendicular to both of them? And cross product. Bam. It's exactly the tool we need for that. Okay, now let's talk about how to prove this. I'm going to show you two proofs. One is to observe that orthogonality is defined by way of a dot product. And a dot product, you can just punch it up, right? You can take this dot product and just directly crank it out, you will get 0. And when a dot product's 0, that means orthogonal. So, I mean, all right, it works, right? Unambiguously, we've demonstrated that these two vectors A and A cross B are orthogonal. But there's a bunch of algebra in there. It's not so bad. It's like 6 terms. It's not the worst thing in the world, right? But whenever there's a bunch of algebra, I feel like that's, at least in many cases, what I'm going to call opaque. In the sense that, what intuition do you gain from the algebra itself? And, it's hard to get excited about that level of intuition. So now let me show you the better proof, what I think is a better proof. And that is to realize, we're going to start off the same way, that orthogonality is determined by dot products. Then notice that this specific dot product is a triple product. Triple products are determinants. Yeah, right? That we just showed. Determinants compute volumes, at least the absolute value of the determinant gives you the volume. So notice we've turned the original question about orthogonality, we've turned that into a geometric question about volume by way of determinant, by way of triple product. There's a lot of ideas that have connected in here, and notice I still haven't gotten my hands dirty. I haven't done any tedious algebra, opaque, cryptic, incontrovertible. Yeah, love algebra, by the way. Algebra is the stuff, right? That's awesome. But it's a little cryptic and opaque, and we haven't really touched that yet. We're just connecting ideas. And so, in some sense, if you want to have geometric satisfaction, not for that fact that this is true, but for the fact that this should be true, right? You just need to convince yourself that when you have a list of 3 vectors, those vectors being A, and B, you just need to convince yourself that the parallelepiped, the 3-dimensional kind of parallelogram-ish kind of thing that's defined by those 3 vectors has no volume. And, well, of course it has no volume. 2 of the vectors are the same. It's got to be 2-dimensional. The whole span of that trio of vectors is clearly 2-dimensional at best, and thus cannot have any volume. So all geometry, right, and connecting ideas to other ideas. This is an awesome little proof, right? There's a lot of good, valuable intuition to be gained by really chewing on and digesting this proof. And so again, you don't have to, right? But I think it's a really good study tool, and will help you digest ideas and understand connections, and that'll help you in just countless ways. Okay, all right, so that's all I have time for on that one. So now again, moving on, when I show you a theorem, again at this point I'm not going to talk through the proofs, I'm just going to wave my hands and hope that what we did with the last one might persuade you that it might be worth a look. So this fact, triple products are invariant under cycling. So notice I just cycled here. And if you cycle this list of 3 vectors involved in a triple product, the determinant doesn't change. Excuse me, the value of the triple product, which of course is a determinant, doesn't change. Okay, so view this however you like. And again, there's an algebraic argument that you can make, and there's also a really slick geometric argument that you can make. And I hope you'll give this a look. There's some nice intuition to be had there. Okay, next fact. Weird one. Hard to see this one coming. Let me zoom it down just a little bit. If you have a couple of vectors and you compute the cross product, the magnitude of that cross product, very weird, but it's equal to the area of the parallelogram that you get that's defined by those two vectors. Really weird. And just for clarification, this notation right here, I'm using that notation just as a convenient way to describe the parallelogram defined by that pair of vectors. So, like so, as indicated. So really weird fact. Again, cool proof. The one quick comment I'm going to give you about, and by the way, another one of my favorite proofs. It's just a beautiful little argument. What I will warn you about with this proof is that there is, at the beginning, there is a big question here of where did that come from? Why are we looking at a determinant of this matrix? Why those three rows is very unclear as to why we're doing it. That does not follow from anything prior. So there is a sort of pulling a rabbit out of a hat aspect of this proof, so the only reason I'm mentioning this is I don't want y'all to get intimidated. I used to get intimidated by this kind of stuff. I never would have thought of that. Why? I guess I don't understand this material well enough because I don't see how I ever would have thought to look at that specific 3x3 determinant. And wrong standard. Right? Don't hold yourself to that standard. This really is extremely clever, and so don't sweat it. I can't imagine most of you would have come up with this, nor would I when I was your age. That's not where you're supposed to be at. Okay. All right. Nevertheless, cool proof. Hope you read the rest of it. Okay. Moving along. Another neat fact. Cross product has something in common with dot product in that when it is 0, you get to draw a cool conclusion. When the dot product's 0, you get to conclude orthogonality, which usually means perpendicularity, which is awesome. When the cross product is 0, you get to conclude linear dependence. So a different conclusion, right? It's more like parallel than it is like perpendicular. Right? Usually means parallel unless there's zeros involved, as opposed to orthogonality, which usually means perpendicular unless there's zeros involved. Right? So analogous in a cool way. Okay, again, cool proof. Hope you give it a look. Another neat little fact. This list, A, B, cross product, is, I'm going to say this wrong on purpose just because this is how you're going to think about it, and that's okay. That this list is in right-hand order. It's okay. Technically, now let me clean that up. It's technically not always in right-hand order because one of these vectors could be 0, in which case there is no right-hand or left-hand order, and so it's not fair to say that it's in right-hand order, right? What I can say on this, though, is that it's never in left-hand order. It's either right-hand order or nothing. Right? Again, casually speaking, most of the time we think of this as being right-handed. The little annoying exceptional cases, understood. Okay, again, cool proof. I hope you'll give it a look. Valuable, interesting idea. All right, so this gives rise, last several things that we've written down anyway, give rise to a pretty nice way to think about cross product, what I call a purely geometric description, based on the fact that everything I have written down here is entirely geometric. This first statement is a statement about, pretty much perpendicularity. I guess there's the occasional exceptions of zeros. That's geometric, right? Talking about the angle between the two vectors, that's geometric. Here's a statement about lengths and areas. That's geometric, right? Here's a statement about order of a list. Again, that's the three-dimensional version of clockwise, counterclockwise. That's geometric, right? So the cool thing about this little description right here is that this perfectly characterizes cross product, right? There is always exactly one vector that will satisfy this list of requirements, right? There is a unique cross product that satisfies these three requirements. And check it out, hardly any algebra at all defining it. So kind of unexpected. I want to remind you, not that far back here, right, we wrote down this wacky formula that seems to kind of come out of nowhere for no reason, right? Very unsatisfying formula. But what we find is that it actually is describing something that's geometrically kind of awesome in several ways, and in fact completely characterized by geometric awesomeness. So, different way to go. What you're going to notice, by the way, in our textbook, right? Our textbook actually starts with this as the definition of cross product. And then by way of what I consider to be some very painful and unpleasant calculations, derives the formula that I started with. Now, so that's just a kind of that's a personal preference. Again, I already told you all I was going to do this in a way that's very different from what the book does. Again, I think mine is more geometrically intuitive and less algebraically opaque. Pros and cons. Okay. All right. So this gives us another cool fact, and that is right here, that the cross product is not commutative. It's a little bit of an unfortunate aspect of cross products. We call it a product. Product sounds like multiplication. Multiplication's commutative. A lot of people, kind of thinking casually or working casually, get a little too comfortable with the idea that the cross product sounds like a multiplication and just assume it's commutative, and it's not. So heads up on that. It's real easy to accidentally, like I say, working too casual and just forget about the fact that it's actually anti-commutative because of that minus sign. Okay. All right. So by the way, how are we going to draw that conclusion? How does this geometric description here give us that? And I think that's worth the gesture that I'll make. So the gesture I'm going to make is also sometimes called the right-hand rule. The phrase right-hand rule gets used to describe actually several different things. Here, by right-hand rule, I mean that if you take your first and second fingers and point them in the direction of A and B, right hand, please, right? And then use your thumb. Now this time you have to make your thumb perpendicular to both of those first two fingers. Then that thumb will point in the direction of the cross product, right? That's the item number 3 there. So if you want to understand, if you want some geometric satisfaction for where does this come from, right? A pretty nice way to see it is that, look, if you list A first and B second, you'd get this. And what would happen if you changed the listing and instead of A first, B second, what if you had B first and then A second? And notice what's happening is just that I'm flipping my hand upside down, which means the direction that the cross product points gets flipped, right, upside down, and thus the minus sign. So, cool little connection. Okay, is everybody all right? Okay. One last little quickie. I've mentioned this before, but cross product is linear. Again, that's a little bit of a sloppy statement. When I mean a cross product thought of as a function of one of the participating vectors, while the other participating vector is a fixed constant, right? So again, that's a mouthful, and so casually, sloppily, we just say, cross product's linear. You have to understand the way it's phrased. So how do we see that cross product is linear? Well, just keep in mind that this function t is that right there, cross product with A. And so the statement that t is linear, there's t, and notice all I have then is a linear combination on the inside compared to a linear combination on the outside. This statement right here is exactly what it would mean to be linear, and not hard to confirm this from what we already know, which I've perhaps seen before about cross products. Okay. All right. By the way, linear on both sides. You can put the fixed vector on the right instead of the left. All good. Still works. Okay, all right. This is the last, the last one. A quickie warning: cross product is not associative, so it's not commutative. Here's the thing about, again, the commutativity. Even though it's not commutative, it is something close to commutative. It's anti-commutative, right? The reason it's not commutative is very consistently, identifiably. It's just a minus sign. Right? The reason cross product is not associative, not that simple. It's just not. It's not even close. There is no minus sign fixed to this. It's just not. Right? So less of a consolation prize. No consolation prize on that. Okay. A couple of quick applications. I suppose worth recognizing that torque can be described as a cross product. I don't know if y'all have seen torque before. It's what I like to call an angular version of force. Force says how hard are you pushing. Torque says how hard are you twisting. So the important physics idea comes up in a lot of physics, a lot of engineering. You may have heard people talk about torque in relation to car engines, right? Some cars have a lot of torque, and they'll brag about how much torque this engine has, etc. Because that's what engines do. Car engines make the drive shaft turn. So natural way to talk about it. So let's see here. I think more importantly, probably, or at least probably more relevant to what most of y'all are going to be seeing, certainly anytime soon, is that magnetic fields, what magnetic fields do is very valuably, very conveniently described with cross products. In particular, that if you have a magnetic field that, let's say, is pointing in that direction, and if you have a charged particle that's moving with a velocity, let's say in that direction, velocity, then we have to throw in the charge as well, cross magnetic field, let's use the right-hand rule then, right? First vector, velocity. Second vector, middle finger, is the magnetic field. The cross product tells you the force. So the direction of your thumb tells you what the resulting force is that the magnetic field applies to the moving charged particle. Right. How we doing? Okay. So again, very important in engineering. Okay. Then I'll also point out, this is annoying, but nothing we can do about this. Very often the charged particles that are moving through the magnetic field, very often they're electrons. Electrons are negatively charged. That effectively, then, if you're talking about an electron, puts a minus sign right there inside of the charge, which means that the cross product of velocity and magnetic field points in exactly the wrong direction, right? Wrong because of the minus sign of the charge. So sometimes people like to fix that by saying, okay, well, yeah, but if it's an electron, if it's a negatively charged particle, then you use the left-hand rule. Velocity, magnetic field. Notice I have to do my hand kind of in a weird way to get my middle finger to point in the direction of the second vector of the magnetic field. Now notice that my thumb points down instead of up, exactly as that minus sign would have it. So when you're dealing with electrons, a lot of people will talk about the left-hand rule. So to me, that creates further confusion, right? I like having one rule, and I know how minus signs work, and that's how I like to deal with that. But anyway, a lot of people like to have multiple versions for specific cases. I just find it more confusing. How are we doing? Everybody all right? Okay, moving along. I imagine that y'all have seen this to at least some of what I'm about to do in section 1.5 here in linear algebra class. They certainly should, but anyway, there's different points of view. The big idea is how do I describe a plane algebraically, plane in space? And first observation I'll make is that if you have what I'm going to call a normal vector, a vector perpendicular to the plane you want to describe, that alone is not quite enough to tell me, for example, exactly which plane I'm talking about. There's a lot of planes that are perpendicular to that one vector, right? But if I say I'm interested in a plane that's perpendicular to that vector and contains a given point x naught, that defines a plane, right? So this information alone, knowing your n and your x naught, completely characterizes the plane. How do we write that down algebraically? And the way we write that down algebraically is with a very clever little quick observation, which is that a difference vector, a difference vector like that, and our given normal vector like that, well, you can just see it right here in the picture. Those have to be orthogonal. And I'm very carefully choosing the word orthogonal, not perpendicular. Orthogonal because x minus x naught absolutely could be 0. The point x naught counts. The point x naught is in the plane, right? So I do want to allow for that to be 0, so I'm going to say orthogonal, and of course orthogonal is defined perfectly by this dot product being 0. So there you go, equation of the plane. Any point x that's in the plane will satisfy that equation, at which you can move things around, distribute and subtract, etc. You can rewrite it like this, which I think is I don't know, I feel like this rolls off the tongue a little better. It's a personal preference. It doesn't matter. No parentheses. That's kind of nice. Right? But anyway, perfectly equivalent. And I also like this one because it's easier to convert into the sort of coordinate form. And that's because, well, keep in mind, n and x naught were both given, so that I can just crank out that dot product. That's just some number. And while we do have the variable x, the point that we're testing, right, whose coordinates are going to be x, y, z, that is still there, and I don't know what those are, but the n is another. It's, well, still given, and because it's given, well, I can just define its coordinates to be a, b, c, for example, and I can just straight up rewrite the equation of the plane in coordinate form as I did down here. So y'all will see this kind of equation here very regularly. One thing I particularly like about this equation is that there's a freebie right here in the notation that, well, you can just take whatever are the coefficients of x, y, z, and, well, that's your normal vector. You can read the normal vector straight off of the equation. That's very handy. All right. One little last quick comment I want to make on the trade-off between these two equations, both of which I like. This is still my favorite one, and roughly speaking, the reason why, and this reason applies in a lot of cases, in a lot of situations in this class. What you're going to find that while many classes that you've taken ultimately boil down to dealing with variables, coordinates, right, scalars, it is bonkers useful in this class to deal with vectors. Vectors, we have sophisticated operations involving vectors. They are powerful, they are useful, they are your friend. And so again, why don't we gravitate toward notations that allow us to use these powerful tools more immediately and conveniently. So I naturally gravitate toward, and I encourage you to just encourage yourself toward vector forms of equations, and don't feel this compulsive need to always kind of crank it out and write everything in terms of coordinates. It's easy to do if you need it, right? At some point in your future, if you really need it in coordinates, yeah, you can do that. But it's unnecessary in most cases. Most of the good ideas connect directly to this form. Okay. So let's do one. Here's an example. This example gives us 3 points. Those 3 points, you will notice, define a plane. There's a unique plane that contains those 3 points. How would I find the equation of that plane? It's a standard, early example of this kind of stuff. Given 3 points, what's the equation of the plane? Now, coming back up to here, the equation of the plane is going to be this, I guess, but so much nicer. Again, as previously discussed, let's think of it this way, because in this form, I can see exactly what I need. I need a normal vector. That's telling me geometric information. The form of the equation there is telling me I need to find this particular vector that has a particular geometric feature, namely that it is perpendicular to the plane that I'm looking for. Now again, I credit the equation for telling us that, not this one. That's all about coordinates. What's B? I don't know what B is. What B is not immediately evident in the picture. Useless. But the vector form of the equation tells me I need the normal vector. It also tells me I need an x naught, namely I need some point in the plane. Now that's kind of a freebie. I've got a bunch of points in the plane, right? All good on finding a point in the plane. I was given 3. Pick your favorite, doesn't matter. I tend to like better numbers, easier numbers. 0 is my favorite. Gotta love zeros. 1 is my second favorite. Right? So take pity on yourself with the arithmetic. Choose the easiest one. Doesn't matter. Okay, so that convenience observed, we're back to realizing that we just need to find a normal vector. So how are we going to find a normal vector? Thank you, vector equation of the vector form of the equation. The way I'm going to find my normal vector is to just point out that, well, it's going to be perpendicular to these 2 vectors in the parallel to the plane. The 2 vectors parallel to the plane I can get by pairwise subtractions, and boom, we take the cross product, we walk away, we won. Everybody see how that worked? Yes.
Where are you getting the b minus a, c minus a?
Yeah. So that's so b minus a, for example, is this vector. Here, let me erase. I've got a mess going here. B minus a is that difference, right? And the whole point to that is because b is in the plane and a is in the plane, that means that this difference is parallel to the plane.
So it's not those specific. You could do like c minus b as well.
Oh, yeah. You've got options. Yeah, that's right. Quite a few different options. So, yeah, you can do c minus a and b minus a, or you can do c minus... Let me do this better. You can do... come on, pen. You can do c minus a and a minus b. Bunch of different options. One that you can't do is you can't do b minus a and a minus b, because that doesn't give you the kind of the 2 different. Yeah, right. Exactly. Yeah, sure. Yes.
Okay, so once we find like that normal vector by taking the cross product of the 2 ones, then we would plug that in to the like n times x and then or n dot. You know what I mean?
Yeah,
equation?
That equation. That's right.
How do we choose our x and x naught?
Okay, so let me put the picture. Okay, so this normal vector we compute by that equation, and it goes there and there. right? The x naught, now we have, the only requirement for x naught is that it be in the plane, and we've got a bunch to choose from, so I'm going to pick A, not that it matters, and that goes there. Yeah? We don't do anything with the x vector.
Oh, because we're solving.
That's the placeholder. That's how the test works. Is that's whatever point you want to test, that becomes x, and so you got to leave that like it is. Yeah. Everybody happy? Yep.
So like x naught is A here because that's what you're subtracting.
Oh yeah, it doesn't matter. It literally doesn't matter. So you could pick. I mean, if you felt like, coincidentally, yes. But if I had chosen C here to be my x naught, different point. But what you're going to find is that this dot product will be the same no matter which of those 3 points you pick. And so all good, go crazy, pick your favorite. Doesn't matter. Yeah.
It's just you'd have to base your if you pick C, you would need to do like A minus C.
Nope, you would not. No, it does not matter. Any point in the plane will work. In fact, if you look at the equation of the plane itself, the equation of the plane, we know we're going to end up with something like this. What it says is that basically any point in the entire plane, whatever point in the plane you pick, the value of this dot product will always be the same. And so that right there is the proof that you can pick any of these points, because it literally will not change the equation. Yeah, that's right. Yeah, sure. Alrighty, moving along. There's a couple of little tricky, little clever observations that I think do need to get pointed out here. This theorem's not in the book, by the way. It is more of a, I don't know if it rises to the level of being called a theorem. Right, but this is a handy little fact that we're going to make use of significantly later in the course, and it goes like this: if there are no y's in the equation for your plane, by the way, super easily observed. You look at your equation of the plane, just visibly look. There are no y's in the equation. Casual glance, right? Then the punchline is something important geometrically. That plane's parallel to the y-axis. So this is awesome, because it's not because the conclusion is unbelievably powerful. It's because the cost, what you have to do to earn that conclusion, is practically nothing. Eyeball glance. No y's in the equation, boom, that's parallel to the y-axis. Right? So, okay, now why is this true? Let's walk through the argument. If there's no y's in the equation, that means there's 0 y. That means that second coefficient that normally would have been called b is 0. That tells me what my normal vector is. My normal vector, you see then, points like so. It has no component in the y direction. And now I make a geometric appeal. That means it's got to be perpendicular to the y-axis. But wait a second, the plane, let me make better color choices. The plane that we were looking at is perpendicular to the normal vector too. So now I'm going to make what I'm going to call a transitivity argument, loosely speaking. The plane is perpendicular to the normal vector. The normal vector is perpendicular to the y-axis. And from that, I'm going to conclude that the plane must be parallel to the y-axis. Everybody see how that works? Cool. So, by the way, there are 2 other very, very analogous theorems. One for when there's no x's in your equation. One for when there's no z's in your equation. Think them through. Draw the corresponding pictures. Think through the argument. Make sure that you can derive and remember those 2 results as well. Yeah.
So this would mean it would be valid for all values of y, right? Or
I don't know what you mean, but the conclusion here is that this plane is parallel to that axis. So the conclusion is about 2 geometric objects. Does that make sense?
Yeah.
Yeah. So this isn't a conclusion about points. This is a conclusion that says that large geometric object, this plane, in fact, is parallel to this large geometric object, this axis. Yeah. Okay. So think it through about the x-axis and the z-axis. Also very useful. Here's another cool example. If I give you a couple of planes, let's say like so, right? Notice that those planes intersect in a direction. That direction, in that direction, there's a unique line that goes through this point A. So the line through that point that's parallel to that direction, namely parallel to both planes, how would we parameterize that line? Everybody see the question? Okay. All right. Now, again, there's a sort of a geometric puzzle aspect to this, but y'all are going to see a bunch of these on the homework exercises where I'm going to give you, the book is going to give you equations of planes or parameterizations of lines or symmetric equations of lines or whatever, and then they're going to ask you, intersect them or look at what's parallel to the this or the that, and then find the resulting equation or parameterization or whatever. So there's a million different ways to kind of combine those ingredients to make different questions. And they all have this puzzle aspect to them, namely, do I cross something with something else, or how do I do it, right? So for whatever it's worth, I am a big believer in pictures in a situation like this. By the way, that is that follows from another really big point, and I think I said this in the introductory recording that I sent y'all, but this class is unavoidably geometric. It is intrinsic to what the course is, right? There is a certain number of students that don't like the geometry, and I understand everybody's different, that's fine. But there is no algebraic workaround that will allow you to just kind of always avoid the geometry in this class. It's not that we have questions and you can use either algebra or geometry to solve them. It's that we are intrinsically interested in the geometry itself. It's intrinsically part of the course, right? So if you're if you are not good at drawing diagrams, drawing things three-dimensionally, right? Well, golly, that's gonna be a problem unless you address it, right? So this is something that's important to actually take an active role in getting good at it, right? Now, everything that I know about three-dimensional geometric drawing, I've put into some recordings that I have on my YouTube channel. Go to the miscellaneous topics playlist. There's like 10 different recordings in there. By the way, that's all good stuff. It's all stuff that I think all Math219 students should know. Very commonly students in Math219 may have gotten here without, for whatever reason. So it's all good stuff, but if you look in that playlist, there's two recordings in particular called Drawing 1 and Drawing 2, and there's a lot of slick ideas and valuable little points of view, etc., that will take anyone, newbie or not, with drawing and give them a lot of good tools for becoming better at it. So I do strongly encourage, take a look. Again, you don't have to, but I think you'll find that useful. Okay, so back to this question. So again, I'm going to use a transitivity here, and the idea is that, for example, this vector that you'll notice I peeled straight off of the coefficients of the first equation there. 1, 1, and 0 are my coefficients, right? So that's the normal vector for this plane, which means it's perpendicular to that plane. Well, that plane is parallel to the line that we're interested in, right? And so that means, connecting the dots transitively, the normal vector is perpendicular to the plane is parallel to the direction vector I'm looking for, and therefore by sort of transitivity, and let me get rid of all the mess here, by my sort of transitivity argument, this normal vector must be perpendicular to that vector. And analogous argument, this normal vector must be perpendicular to that vector. And so just like we have done before, when you have two vectors and you want to find something that's perpendicular to both of them, which we do, cross products, yeah. Is everybody all right with that? Okay. Yep.
Are the two planes perpendicular to each other?
Nope. Don't have to be. No, they don't have to be, because as long as they're not parallel to each other, which again we can see very easily, because if the planes were parallel, then their normal vectors would be parallel. These obviously aren't, right? So yeah, so as long as they're not parallel, any two planes will intersect in a line, which defines a direction, and that puts us in business. Yeah. All right. Okay, and again, it's all over, but the details, again, we were given A. We just talked about how to compute V, and once you have the A and the V, that's how you parameterize the line. Okay. Okay, now you're going to notice in both of the examples that I just did, I'd made what I was calling transitivity arguments, and very cool, very useful, and there's lots of different versions of what you might call transitivity arguments. So the big warning here, and this is something to be extremely careful about, not every seeming transitivity statement is true. So heads up, think it through carefully. I want to emphasize, I'm not warning you against making these kind of transitivity sort of arguments. You kind of have to, right? It's part of the geometry that we're going to need to be able to connect the dots, right? But please do always be careful, because things that look like they ought to be true very often just straight up aren't. And so a couple of examples here. If a vector is parallel to a plane, if that plane is parallel to another vector, I mean, it kind of feels like those vectors ought to have to be parallel, but nope, they're not. Right? Case in point right here. So that doesn't work. Don't make that argument. It'll give you garbage. Likewise, another one, this one's a little bit less obvious, but if you have P is perpendicular to Q and Q is perpendicular to R, yeah, no conclusion. P and R, not only are they not perpendicular, they're also not necessarily parallel. That's just nothing. Again, no conclusion. Yeah, go ahead.
Are these like statements in general, or just for these specific situations?
You mean this right here, for example? Or
is that like always true?
No. So I don't mean to say that they can't be parallel. What I'm saying is that you can't conclude that they're parallel. Yeah. So it doesn't follow.
Okay, because of these specific things that could happen.
Yeah. There's just too many different. Yeah, that's right. Exactly. Right. Okay. So heads up. So by the way, my rule on this, I mean, I thought at one point of like enumerating every possible version of a transitivity argument, and I just started thinking about how many different versions that would be, and I don't think it's at all a good idea, a good investment of anyone's time to try to memorize all of the valid transitivity arguments and all of the invalid. And even if you did, you wouldn't remember that, right? 10 years from now, there's no way. Right? So I emphasize you have to think it through geometrically. And that's, by the way, that's the rule in this class on a homework exercise or on an exam question. The rule concerning transitivity is go ahead, make all the transitivity arguments you want if they are true, if they are valid. Right? So think it through, make sure it is, and then go ahead. You don't have to prove it or anything like that. Okay. How to parameterize a plane. We've talked about parameterizing before. Again, keep in mind parameterization means we're talking about a point generator. So in goes a parameter. We're going to momentarily talk about the possibility of two parameters. But parameter in points out. Right? We're generating points. So let's talk about how I would generate points. For example, how would I generate this point on a plane? And let's suppose I know certain things about the plane. Perhaps, for example, I know a point on the plane. Right? And suppose I know as well a couple of vectors parallel to the plane. And quick observation, if you know a point on your plane and two non-parallel vectors parallel to the plane, that defines a plane. Right? There is exactly one plane that has those three features. So the way we're going to generate then this point, how are we going to make that happen? Well, we're going to start at the point that we're given, and then we're going to move some amount, some multiple, right? Some to some extent in the v direction. So that'll be, of course, a scalar multiple of v. And then from there, we're going to move some amount in the w direction. And, of course, that'll be a scalar multiple of w. And I claim this will do it, right? If you give me a starting point in the plane in two different directions, and I can move as far or as little as I want in both of those directions, yeah, I can get anywhere in the plane. Yeah? Everybody see the geometric? By the way, you'll notice the similarity to one of the homework exercises that's due tonight. Right? I forget which one. I want to say it's in section 1.1, maybe. Is it the first question? Yeah, okay, yeah. So this is a, if you were having trouble with that, just something to think about there. So now, of course, in that exercise, you have to restrict the values of S and T, and you think that through. But anyway, the point is this parameterizes the entire plane, but it does so, you'll notice, with two parameters required, right? I need both S and T to be able to make this work because I need to be able to control how far I'm moving in each of the directions. And so, by the way, this generalizes. Not only will two parameters by way of this construction generate a plane, but two parameters by way of other formulas that we're going to talk about later in the course will generate surfaces in general. So for the moment, we're not going to do parametric surfaces, but later on we will, and it's different details, same basic idea. Yep.
Do V and W need to be perpendicular here?
Nope. All they need to be is not parallel. Yeah. Because, it's tempting to, when things are perpendicular, life is good in certain ways, right? There's certain conveniences about coordinates and dot products that come up when you have an orthonormal basis. You may remember from linear algebra, yeah. But in this case, whatever. All good. Yep.
So here we also need to have boundaries for how.
No, not here. Okay, so there's an awkwardness about how we draw a plane, right? So this is my attempt at drawing a plane, but it looks like I've drawn a parallelogram, and that's not what we mean by a plane. When we say a plane, I mean, extending infinitely in all directions. Right, and so I don't know how to draw something infinite. So hack, but I talk about in the recording, by the way, about drawing. A hack we use is to draw a plane. We draw a rectangle sitting inside the plane very often, and then that ends up looking on the page like a parallelogram because we're looking at it at an angle, right? It's just one of the weaknesses of drawing is that sometimes the same drawing kind of looks like different things. Yeah, right. Okay, all right, moving along. Quick example. Same 3 points that we were looking at before. We already talked about how to find the equation of the plane. Let's talk now about how to parameterize the plane. And keep in mind, what you need to parameterize the plane are, well, you need to have a starting point. So you need some point in the plane. Cool, I have 3. Pick your favorite. I kind of like the one with the easier numbers. Not that it matters. Pick any point you like. And then I need a couple of vectors parallel to the plane. And, okay, well, we can, again, pairwise subtract to get a vector parallel to the plane, and then again get another vector parallel to the plane, and we're in business. We have ourselves now a parameterization of the plane per above. Okay, so there's various related questions called distance problems. This is another sort of kind of a puzzle question, right? Of given certain information, how can you cleverly use known operations to conclude certain kinds of information? And in this case, we're there's a bunch of questions that all fall in the same category of how do you find certain distances. So I'm going to show you a few of these tricks. Again, this is not a complete list. But this is, once you get a hang of the certain kinds of tricks that you can pull, right? Then, that's a foot in the door, and you can kind of start putting pieces together. And so here we go. Suppose I have a point, and suppose I have a line. And suppose I want to compute the distance then from the point to the line. How would I compute that distance right there? There's a couple different ways you can do this. I like this one pretty well. Notice that the first thing I can do is I can take the point that I'm given. I can take any point, doesn't matter, any point at all that's on my line, and I can subtract to get what I'm calling W, which does not tell me the distance. Next, I can talk about the projection of W in the V direction, in other words, in the direction of the line. We have a formula for how to compute projections, right? That is not what we need to compute the distance either. But between the two of them, notice that if I subtract, if I take W minus W minus the projection, that difference, doesn't matter what x naught you pick, that difference will always be then perpendicular, and therefore that is the vector whose magnitude gives me the distance that we want. Yeah.
What is the difference between that x vector and that w vector?
Yeah. Okay. So x is a I'm thinking of x as a point.
Oh,
right?
It's not a vector.
Well, right. It's not a vector. There is always this issue, though. I mean, you got to keep in mind any point can be thought of as a vector in the canonical way, where because you have a point, you can make an arrow with its tail at the origin.
Okay.
And draw that arrow to where the point is, and that's what we call the corresponding vector. Sometimes we call that the position vector, right? Okay. So whenever you have a point, you can think of it as a vector. So let me fill in some blanks here. If I were to imagine the origin being, just for geometric convenience, I'll put the origin here. If that's the origin, then this point could be thought of as that.
Yeah.
And this point could be thought of as that. And then the difference, now you can see that's literally a vector subtraction that gives me W.
Okay.
Yeah. Are you happy with that?
Yeah.
Okay. Cool. Great. All right. Here's another way to do the same problem. And there's other ways beyond this as well. But this is another clever one. This is what I like to call a mathematical bank shot, I'm making a reference to pool. I don't know if y'all are familiar with pool, 8-ball, that kind of thing, right? So sometimes if you're here and you want to go there, sometimes you start by going that way, and then it bounces off the rail and then goes where you want. So this is a mathematical bank shot in the sense that we're going to start off by computing something that's not what we're interested in. So in particular, I'm going to start off by computing this area right here. They didn't ask about area. Why am I computing area? Well, the reason that I'm going to compute this area is because if I compute it two different ways, the answers that I get, being as they are both equal to the area, they are also both equal to each other. And sometimes this is awesome because sometimes the thing that you're interested in is involved in that equation, and now that makes it easy to solve for. It's a real clever move. Compute something two different ways. Compute something you don't care about two different ways in such a way that what you're interested in shows up in one of the calculations, and then solve. Many examples in math of this kind of an argument. So the first observation to make is that the magnitude of the projection times the distance that we're looking for gives us the area. And then the second observation I'm going to make here is that the cross product of these vectors also gives you the area by way of its magnitude. And there you go. And then you solve for distance. So that works too. It's another slick move. Nice idea. Here's a tricky one. Suppose I have parallel planes. Now, when am I going to find parallel planes? Parallel planes will have the same normal vector, right? Or at least their normal vectors will be parallel, whatever. Okay. And again, suppose I want to compute the distance between these parallel planes, and so the distance in this case would look something like that. Notice that geometric observation here. By the way, there's a lot of this in this course. Geometric appeal, you can just see it from the picture. That distance between the planes is itself perpendicular to both of the planes. Okay. So so the slick move here is to realize that, well, in fact, because it's a distance in the perpendicular direction, and because the normal vector is also in the perpendicular direction, this distance is mostly just a component. And you can pick any vector you want here. I arbitrarily picked a couple of points A and B. It doesn't matter. Any points you like, and in these, one in each of the planes. Subtract them. Probably won't be perpendicular. Probably won't be something whose magnitude gives you the distance. As I've drawn it here, it's all wonky, pointing in the wrong direction. But if I look at that vector and its component in the normal direction, I get exactly what I want. Everybody happy with that? Again, slick move. Nice to have all these tools in our toolbox. Oh, one little quickie. I do want to remind you that component is a coordinate, kind of. It can be positive or negative, right? But distance is not. Distance is an intrinsically positive thing. So I was being deliberately in my defense, but I was being a little bit sloppy when I said that the distance is a component, because they are these, again, sort of intrinsically different things, right? And so what I can say, though, what is true is that the distance is the absolute value of the component. So you do have to be careful with that, right? Just make sure to think it through. In this case, as I have it drawn, the component would be positive, because you can see right there, there's that difference vector, there's the component, it is in the same direction that the normal vector is pointing, and it would be positive as it is. But if you had picked the vectors and subtracted them in the other direction, your component will be negative. Nothing wrong with that. But it's not a distance. Okay. All right. Last little example. This is a really slick move. Again, this is one of these ones that I never would have thought of myself. And again, please don't please don't have the wrong yardstick for yourself. Please don't compare yourself to would I have been able to think of this on my own. This is a very clever move. I don't think I would have thought of this on my own. Somebody showed this to me when I was in a comparable class. For your consideration. Suppose you have two skew lines. Just in case you might not remember what the word skew means that the two lines in 3 space do not intersect and are not parallel. In other words, the way I like to think of skew lines, they're lines that have absolutely nothing in common with each other. They don't have any common points. They don't have a common direction. They're just random, unrelated. Okay. All right. So, oh golly, this is a tough one in the sense that if I want to find that, first of all, how do we even define the distance between two skew lines? Do I just pick a point here and a point there and just, is that the distance? Well, no, because look, there's a bunch of lines from that point to the other line that surely I want the shortest one, right? So, okay, so can I say that it's that distance? Well, no, because from this point, I didn't draw that very. Here, let me. From whatever is the right point on this line, there's a bunch of different distances that you could compute to the other line, and again, I want the shortest one, right? So, geometric appeal. You just got to sort of think this through on your own. The answer then is going to be that we're going to look for a distance from a point on one line to a point on the other line that's perpendicular to both of the lines. Now you just have to chew on that geometrically and persuade yourself that, yeah, that kind of has to be it. Is that satisfying geometrically? Okay. All right, with that noted, here's the slick move. Again, I wish I'd thought of this. I did not. Somebody showed me this. But a real slick move is to realize that if I take these two vectors and cross them, the cross product is going to be perpendicular to both of these lines. So then if I use that as a normal vector, that will give me planes that are parallel to those lines. And if they're parallel to the lines, if you think about it, now again, another geometric appeal. If a line and a plane are parallel, they either don't intersect at all, or the line is entirely contained within the plane. And so punchline is, with this little move of, let me clean up my mess, with this little move of taking the cross product of those two given direction vectors, I can produce a pair of planes parallel to each other that contain the two given skew lines. And so our weird and creepy question of, oh my gosh, I don't even know which points to look at to find this perpendicular distance, turns into just, well, find the distance between two parallel planes. And good news, we already know how to do that. If I can get my thing to cooperate here. Here we go, yeah. The distance between two parallel planes. Old news. Yeah.
So even though the skew lines, because they're not parallel,
Yep.
they can still be contained within parallel planes.
Yep.
Kind of,
It's very unexpected. Yeah, that's right, and that's why I say I never would have thought of this myself. Right? I don't know. Maybe I don't want to credit myself for being that clever, though. It's possible, but I wouldn't assume it. So clever idea. Everyone gets to benefit from whoever was the first smart alecky person to think that up. Right? It's a real slick move, but it's true. Right? Does that make sense?
yeah, it's not just kind of like
Yeah.
not
Yeah.
quite right.
Yeah, that's right. You gotta sort of choose. Think through the argument though. Again, about sort of the transitivities. If the vectors are, let's see here. If the vectors are perpendicular to the normal, and the normal is perpendicular to the planes, that means the vectors are parallel to the planes. Yeah. Right. Okay. Like I say, slick move, very clever. Okay, moving along into 1.7. We'll just do a little bit of this, and then we'll have to call it a day. So let's talk first very briefly about what rectangular coordinates are. I know y'all know rectangular coordinates. It's this picture. Y'all probably have known this since, 6th grade? I don't know. I'm not sure when they do that anymore. Anyway, y'all have seen this a long time, very familiar idea. I'll point out that what this means is that if you give me a pair of coordinates, that produces then a point in the plane. Okay. It also is the case, now this is a different observation, but it also goes the other way. In other words, coordinates are unique. Given any point, there is a unique x-coordinate and a unique y-coordinate. You can't have multiple xy coordinates for the exact same point in the plane. Well, of course not. Right? All right. So that uniqueness is what we're going to have to get ready to let go of, because we're about to talk about some new coordinate systems that are not rectangular. We'll define those in a few minutes, or more than likely next week. But they are not unique. And so this is a luxury of rectangular coordinates that we will not have to our advantage in coming up real soon. Okay, another cool thing about rectangular coordinates. These are, again, old news. I know y'all know this one, that the standard basis vectors have this nice feature that the coordinates of a vector happen also to be the coefficients in how you write that vector as a linear combination of standard basis vectors. Well, sweet, right? That's neat stuff. Very handy. Closely related fact, if you're doing algebra, linear combinations of vectors in rectangular coordinates, you can just do them one coordinate at a time, right? The first coordinate, do that same linear combination in the first coordinate. Same linear combination in the second coordinate. Awesome. Right? You can do linear combinations of vectors by linear combinations of coordinates. We've been taking that for granted for a long time. Right? At least all through your linear algebra classes. Again, that's a luxury. That only works in rectangular coordinates. It's just not true in other coordinate systems. So heads up for that. So let me just real quick wave my hands at what polar coordinates are. Y'all have probably seen pictures kind of like this before. The big idea I want to throw at you is that I like to think of r and theta in relation to a function. Think of an r theta plane over there on the left, and that there is this function that if you give me an r and a theta, then I can produce a point in the xy plane. And the way this function works, well, it's exactly what you think it is. The theta tells you an angle. That defines which direction we're going in some sense. R then tells you how far to go in that direction, and that gets you to the point we're talking about. Right? right? So this is one way to think about polar coordinates. Now again, it is tempting to think of polar coordinates as being something that you see right here in the plane, and in fact that's even okay in a lot of senses, but I think it's very valuable to think of the function that does this, and it's not hard to persuade yourself what that function is. Whoops, let me get this to do this. The trigonometry of this triangle will persuade you of these formulas down here. And again, I'm assuming that y'all are all perfect with your trig. By the way, make sure that's true. The prerequisite trail of this course gets used heavily, so make sure you're solid with trig. And easy to draw these conclusions here. One last little comment and we'll call it a day, and that is don't get too comfortable with the idea that r is a distance. It's not necessarily, because keep in mind r could be negative. Right? If you're talking about in this direction, what does it mean to go negatively in that direction? Well, negatively just means go backwards. There's nothing weird about that. It's perfectly legal for r to be negative. I am very aware that a lot of y'all have been told by high school math classes that r is required to be positive. They made that up. Right? In general, r is perfectly allowed to be negative. So don't. And again, negative can't be a distance. So tempting to think of r as a distance. It's not. It's a coordinate. It is allowed to be negative. Distances are not allowed to be negative. So, like I say, a little fine point. Okay, we're going to draw the line right there. Y'all have a great weekend. See you on Monday.